Hello, I'm Patrick Pryor, and this is my Physics 2212 lab number 4, circuits. So, intro. For this lab, we're trying to predict the behavior of circuits with resistors. We're using multimeters to measure the values of current and potential differences. And some fundamental principles are Ohm's law, the loop rule, energy and charge conservation, and resistance in series. So some of the assumptions and our model is that resistance is negligible with wires, and resistance is negligible with an ammeter. So we made a model of a circuit to observe the behavior of resistors and capacitors in different combinations. Here's circuit 1. As you can see, we calculated the current of I1 and I2. So circuit 1 and 2, as we did in lab, here are some of the pictures of us doing it in lab. So when we also modeled these circuits online and plotted the log of the change in potential over the initial potential energy versus time. This is the graph that we got. So as you can see, there is a voltage drop in our circuit as it's going throughout it, because the voltage is going to drop with time. It's going to start off stronger and slowly get weaker. So some of the assumptions and sources of error is that the resistance of the wires is negligible, and conditions usually aren't perfect. It can be a human error, and the hardware is pretty heavy, and it's used a lot, heavily used, so it can cause different wear and tear. What if? So using a real ammeter versus an ideal ammeter. So an ideal ammeter in the simulation is assumed to have zero internal resistance, so it doesn't affect the circuit it's connected to. A real ammeter has a small but non-zero internal resistance. This resistance can slightly alter the current in the circuit because it adds a small resistance to the overall circuit, potentially reducing the current slightly. So the impact on the circuit is that if you were to use a real ammeter in your physical circuit, the current measurement would be a bit lower than an idealized virtual simulation due to the additional resistance. This could result in a minor change to your experimental observations. And then if you have a virtual versus a real circuit, it's that when you compare the real circuit's behavior with the virtual simulation, you should notice that a real ammeter slightly alters the current in the circuit due to its internal resistance. In contrast, the virtual ammeter doesn't influence the circuit at all, as it's modeled as ideal. So what if you were doing this lab in real life and using an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? If you did this lab with the real circuit components, access the virtual circuit link above and see if you can determine how blah blah blah. Ideal model prediction. An ideal model, if you connected a real battery directly to the capacitor with no resistor, the capacitor would theoretically charge almost instantaneously within a negligible amount of time. This is because there's nothing to slow down the current from the battery to the capacitor. What happens in real life? In real life, the charge will not happen instantaneously even without a resistor. Factors like the internal resistance of the battery and the wires, as well as parasitic resistors and inductors in the circuit, would slow down the charging process. Real charging time. If you perform an experiment with a real battery and capacitor and measure the charging time with an ammeter, you would observe that the time taken to charge the capacitor is longer than predicted by the ideal model. This is because the real-life components are not ideal and have properties like resistance that affect the time constant of charging. That's my lab. Thank you for watching.